Hi everyone, welcome back to the channel. Today I'll do a video on database indexes. I think it's a very important subject that people need to learn if you're working with databases, because they can critically speed up your queries and just make your application run way better. This is applicable to any database, relational database systems, but we're going to use PostgreSQL today in this video to showcase basically what we're doing. And I'm going to be able, after the end of this video, to understand the basics of indexes and how they can help speed up your application. I'm going to talk about the B-tree index today in PostgreSQL, but it's also applicable to any other managed database system like Neon or Supabase or any of them. So without further ado, let's get started. So the first thing we're going to want to do to get started is just have a base table. So I'm going to show you what I did. So if you look here, we basically have the employees table, which is a table I created for this video. As you can see, we don't have any other indexes than the main ID column. So right here, we can see that I have those columns made. I have an ID column, a name column, a title column, seniority. So if we look at the schema, the ID column is going to be automatically generated every time there's a new row inserted, right? So it's a int 4, so just a 1, 2, 3, 4, 5 and increments. The name column is a type text that is not null, and the other ones are also the same not null constraint. So the name will be the employee name, which for this example will only be employee underscore 1. And then the title will be basically the job of the employee, so backend engineer, let's say, but there's different data types. So this table has multiple million rows, so in this case it's going to be quite diversified. Then the seniority is going to be a number, a random number. So as you can see, there's basically just a number of years that the employee would have been working at the company. So without further ado, just before we get ahead, just understand that right now the only constraint that there is a primary key constraint. So it automatically creates an index by the nature of it. And if you can see, the access method is B-tree, which is going to be the index we're going to talk about today. So without further ado, let's start with the example. So I compiled a bit of examples to show you guys the base goals of different indexes that we're going to use. And I'm going to show you guys how you can interpret those results and analyze the speed efficiency and if it's worth for a specific index to be used. So first thing we're going to start like without any index, so just a baseline result. So one thing we're going to do, as you can see right now, we're just going to do a select star queries from the employees table with a title backend engineer. So this is going to allow us to basically get a specific title, and we can actually group it by the title. So if we do title, and then we can do a count star, and then we can group by title. It's going to allow us to basically count the differences of different titles. So as you can see, backend engineer has 99,000 basically rows, and the others have about the same amount. So we don't care about that, so we can close that. Now we're going to show how quick it would appear with the explain analyze command in front of SQL of select star. I'm going to show you what the results are for this. So this is the way you interpret basically any any results in Postgres in terms of a query preparation and execution. So as you can see here in the query plan, there's a thing called sequential scan. Okay, so a sequential scan is basically the way that any relational database system will just basically go row by row and try to find the value you're looking, right? So in this case, it's looking for title equals backend engineer. So what it would do is it would go in this table, go to data, and row by row try to find a row having the title backend engineer, right? Which is really inefficient, because if you think about it, if there's no backend engineer row, before the 10 millionth row, it's still going to scan the whole table, which is really inefficient and it's going to be very long. So basically we can see here we have tech lead. So if we check with tech lead, it's going to be longer, right? So right now it said execution time 100 millisecond, but if we search for tech lead, just like this, and let's run that, you see it took 30 milliseconds more just because tech lead is farther down in the list of IDs, right? So sequential scan is deeper and needs to go deeper to find the same result. Now let's get back to our backend engineer example. And as you can see, basically right now what it's doing is only a sequential scan. There is no index. The only basically filter that was done is the backend engineer text, but otherwise it will still need to filter all those rows basically based on backend engineer, right? So it will remove the other 900,000 and then scan the 90,000, which is really inefficient. So we don't want that in any database system because that just involves more IO, more CPU time, more memory. So I'm going to show you how we can optimize this, right? So I'm going to show you the first example I have for the index. So the first one is going to be the B-tree single column index, which is really a basic index. And I think it should be at the minimum an index that every database has, every table has, because it's really simple and you really don't lose anything by doing that. And it's going to help you make your indexes way faster. So let's just create the index now. So the goal of this index is basically to create an index on the title column. So think an index as a dictionary, right? So let's say you're trying to find the phone number of a barber in your city and you were in the 80s or the 90s, whatever, you would use a phone book where the phone book is sorted by alphabetical order, right? So the way you would do it is, if you're looking for, Stefan as your barber, you go to the S section. So you go to the S section and then you just filtered out basically 90% of the rest of the results. And then you just look for the second letter being T, stuff like that. So that's how an index works. It basically uses your data as a dictionary. So when it's time to retrieve, it's faster to do, right? But the thing is that it needs to store that index. So that index is stored alongside the table, not inside the table, but alongside the table, and is usable independently of the table. So we're just going to create the index, and you'll see it's going to take a small time. So it took about half a second because it basically needs to take all the rows and create that dictionary that I just talked about. Now, for now, we're just going to stay, we're not going to touch the cluster thing. I'm going to touch on that later. But let's see how fast it goes with the index and without the index. So if you remember, here we had, 100 millisecond. And now we're going to see what it's going to do with the index. So if you look here, it's basically cut the execution time by 4 times. And you see the difference in the query plan, right? So if we look in the query plan, what we're seeing is instead of seeing sequential scan, we're seeing bitmap, heap scan on employees. And basically the thing that is looking in the index is the title, right? So it's using backend engineer to filter out your dictionary that we just talked about. And after that, what it's doing is it's scanning the index instead of sequentially scanning all the filtered out rows, right? Which is way simpler. And because of that, it just reduces the number of reads that it needs to do with the buffer, which is really the most, costing part. So this simple index just saved us 4 times the execution time, which is pretty impressive for just something that is, is free in your database and is not going to cost a whole lot, right? So that's the basic example you can do. So the B-tree single column index, pretty simple command. You just select the column you want to use for the index. Now I'm going to show an example of maybe you want, the title, but you also want something else, right? So maybe you want the title and the, the name or something like that. So In the next example, I'm going to show you what a composite index is. And basically, the composite index is basically the combination of two different columns, right? So like I said, maybe, so in this example, I have the seniority and the title. So maybe what I'm really interested in is knowing for backend engineers with more than 10 years of seniority. So what I need at this point is take those two columns and build an index, a dictionary that combines both, right? So it's like, let's say we come back to our phone book example. Let's say in my case, I'm looking for a barber named Stefan, right? So you could have an alphabetical order, table of contents that says the name, and then in parentheses it would say the job of the person, right? But what you could do is, like I said, filter with your own eyes the name and also the job of the person at the same time, so you're going to find faster your desired row, right? Or your desired employee in this case. So I'm going to show you basically before and after. So again, let's run the query without the composite index. So again, let's take a small screenshot here to be able to compare. So we're going to put that here. So we are at 27 milliseconds, so about the same time right now as the previous query with one index, because it's basically just searching for that and then after that filtering based on the value. So you can see that it removed by the filter again, which is something we don't want. We want to use an index for that. And after that, it uses the index scan, which is good. But in this case, it's using, just a full table scan to find for seniority above 10, which we don't want. So now let's see what it does with the index that we have here for title and seniority, which we wanted. So if we create that, it's going to take a few seconds. So about 1.2 seconds, which is not bad. And then if we do the explain analyze, so as you can see right now, it reduced the time to execute, I'd say by probably about 30-40%, which is pretty good. So what it did is it basically, as you can see, it removed the filter. So it's not filtering rows because the index already does that filtering for you, right? It's a stored state of filtering. So you can see that it also reduced the number of hits for the buffer, which is the goal here, and reduces the total cost of the query itself. So as you can see, the index was searched. And basically the index needs less search because since you have multiple filters inside an index, it's going to be intelligent enough to look based on those two things at the same time. So again, we basically saved a whole bunch of time by just adding a composite index, right? So again, like I said, if you do this, you're going to save time, but not as much as if you were looking with the seniority, because that's only going to use one index. With the index is going to be the index that we previously defined, which is IDX employee's title, but it's not going to be able to use the index for the other part, which is the seniority, right? So this is why you need to use both of them at the same time with the where query, so that it's going to be as efficient as possible. Again, same thing. This one is also not going to fully benefit from the the full index because you're only filtering based on seniority, and we don't have an index for seniority, right? So in this case, it's still doing a sequential scan of employees, and it's not a match scenario, so it's not doing an equal operation. It's only going to do a numerical comparison, which is even more costly than a text comparison. So you can see how the composite index can be used if you know you're going to use two columns, but it's not going to be relevant if you're only using one. So at those kinds of spaces, you might want to use a single column index based on your strategy. All right, so now what we're going to do is basically talk about a covering index, and just again, we're going to use another example. So it's going to be on the name and the seniority, and I'm going to show you what it's going to do. So I'm just going to create the index. And then what we're going to do, we're going to run this. So in that case, what you see is we're selecting the name and seniority, but we don't have a, we don't have a filter for the name and seniority. So what you can see here is that, again, it partially used the index for the index scan on the employee title, but it didn't use it for, the rest, that is selecting the name and seniority, because we don't have indexes for those, right? So you're still able to cut a lot of the costs, but you're still going to use some execution time to select those values, right? Which, if you're selecting those values a lot, you could create a composite index on, name, title, and seniority, which would be a bigger dictionary. But again, if you're doing that query a lot of times, that would be really useful for you to query that index. So that's another example, basically the coverage of indexes and why sometimes having composite indexes is not the right way to approach it. Because also think about it, like an index is going to take storage, right? So even if it takes 20-30% of your storage, it's still storage added that is not necessarily necessary if you don't need to query that specific column, right? So if you make a composite index on name, seniority, and title, but you're only really wanting title as the result, then you're wasting, some compute space and some storage that the index needs to be looked on every time you do that query. So you got to think about it when you choose a specific index strategy. So now I'm going to show you a partial index. So let's say I'm someone who has a company like this, and this is the list of my employees. And let's say my goal is to give a raise to every employee that has a 10-year or more. So in this case, I had put 10-year or more experience at the company, because we're doing a 10-year anniversary raise event, which what I would want to do is find, that number, let's say every year, where I want to find those employees that surpassed my, the awaited 10 years delay for that raise. So what we're going to do then is we're going to do what we call a partial index. So a partial index is basically an index that, instead of doing for a full column, it's going to do it for a specific number of rows of that column based on a criteria, right? So we could create an index on seniority, but seniority only where it's equal to 10 or more years. So if we create that here and then we query that, it's basically going to show you what would be the cost. So again, you see we use the index, so the IDX employee senior staff that we just created. And as you can see, it's still 300 milliseconds, but it's still faster than if we would have used just a seniority on more or equal to 10. So we can remove the index and see what it would have given us. So if I go here, I open the table, indexes. Now I refresh. You can see I have my indexes that we created. Let's say I remove that index like that. Then I can save that. And if I go back here, let's just take that in screenshot. So you see this is with the index. So we have it with the index, 300 milliseconds. And now if I go here and I run this again without the index, you can see it's 447 milliseconds. So again, it took more time. And it's going to vary, depending on if you're using an index or not. Like right now, you see it's using the index because I just recreated it. But if you don't use an index, you're going to save, you're going to basically cost more in terms of sequential scan, right? Which we don't want. So again, this time we saved probably 100 milliseconds. So depending on your query, you're going to save a different amount of execution time every time. So now if we continue and we do a expression index, so I'll give you another example of what you'd want to do. So in a bigger table where you maybe don't have, data that is clean, data that is, clean and just regularized, normalized, you maybe want to do something where you have, rows where you have employees, let's say in uppercase and lowercase, just not sure which one, you should keep. You don't want to touch the raw data. So what you would do is create an index that does this for you, right? So it basically stores the normalized version of your data and maps back to that denormalized version of your data, right? So let's say, for example, we want to find the titles of employees, so a backend engineer, but we don't know if it's stored as, uppercase, or maybe it's stored as both, but you want to know only the, merge the two results together, right? So what you would do is you would create an index basically on employees, but you lower the title so it's usable whether it's uppercase or lowercase. So let's just do that. And as you remember, if we look in the the index section, we do have a index employees title that we just created like this, so the lower title, but we also have one for the title, right? So this is really important to know how Postgres is going to basically use this index engine to find the difference between which index to use in those two cases, which are very similar but different, right? So notice we have lower title, and we're going to see that it's going to choose to use the lower title one. And this is a plan that is being done, at the planning time. So the planning time is this, right? The Postgres planner basically looks at what's the shortest path to a specific result, and it looks across indexes, partitions, clusters, whatever, to find what's the best, path to that. Now, as you can see, the execution time is pretty quick, so 29 milliseconds. And what it did is it did an employee scan, basically a heap scan on employees, because it needs to return all columns. But if you look, it did an index scan on the index we just defined, which it basically got to filter out a whole lot of rows, just because we could filter with lower title, backend engineer, and that gave us a lot of efficiency. But what I wanted to outline here is that it chose the right index, right? Because if we use the other index, it's going to be slower than if we use the lower index. And it's probably going to be a marginal, cost efficiency, but it's still going to be an efficiency that we could have, went around if we didn't use an index like that. So another good example of how you could use an expression index for specific use cases of data. And so this one, we're just going to show the primary key index. I'm going to show you, if you were to choose an employee with a specific number, you can see that it's going to scan the primary key. So when you have a primary key, it's already indexed itself, right? So you don't need to create another index on top of a primary key, because itself is already an index by the nature of a primary key. So just wanted to let you guys know you don't need to do that. And then I'm going to show basically the ordering and the limits for indexes, and how it's going to allow you to, get data quicker if you're using those, right? So in this use case, let's say we'd want to, maybe every 3 months find, all the employees and look what's the seniority of each employee. So what we want to do is do a select star from employees, order by seniority, and only get the top 20, let's say, right, to put them on the board or whatever. Now, if we wanted to do that, without an index, what we'd want to do is we basically start by, sorting all the data. So a sort is actually pretty, expensive in terms of costs, because it also requires a parallel sequential scan to check each value and then move them up or down on the list depending on the new value that was just added. So if we look here, we're sorting by descending, so the highest at the top. And then what we're doing is taking all those results and basically taking the other columns and merging it to that, and then taking only the top 10 rows, right? So we're seeing 100 millisecond time here. Let me open that. And now let's create an example with this index to store it as descending. Now let's run it again. And as you can see, it's instant, right? So we went from literally, 100 milliseconds to not even 0.1 millisecond. So the gain here is, in the 1000x levels. And what you can see is that the query is way simpler, right? Because we already have that dictionary created, right? We already know that the seniority numbers are at a specific place. And since we only need the top 20, sorry, we're going to go from the start with the highest ones, right? So we don't need to scan the whole index and get only the latest one, right? Because let's say if we wanted to do an index that is reverse, which is ascending, and then we select by descending, it will be longer because that seniority is stored at the lowest of the index, at the lowest level of the index. And then after that, we query by the descending, so it's not going to find it first. So in this case, we're really saving a lot of time. You can see all the operations are also way simpler. So we're just scanning the index, and we only got 5 hits, and it was pretty quick. So another good case of indexes here. And then we have the index clustering. So that's kind of bonus section I wanted to show what you could do with the indexes. So let's do a index clustering for the seniority. So we're just going to do a simple index. Nothing changes at this point, just the seniority index. And then what we want to do is check before the clustering. So just a simple query like that. We can see we have a simple index scan right here that shows us the results. So about 87 milliseconds, so nothing super crazy. And now what we want to do is cluster that specific index. So when you create an index, like I told you, it creates a dictionary, but it doesn't mean that the dictionary is ordered and grouped by a specific value, right? So we basically said between here between 10 and 15. So what it would do if we create an index and then cluster it is that it would group those index into sub-indexes, so clusters, based by year, basically. So then you'd be able to search way faster with a year filter, right? So if we do the cluster, just like this, it's taking a little bit longer because there's millions of rows to scan and cluster together. So about 5 seconds. And remember, it took 87 before the clustering. If we just analyze employees, just to make sure it takes into account the new clusters. And then we do the explain analyze, just like this. You can see, again, we saved about 15, 16 milliseconds because it doesn't need to filter as much. It doesn't need to filter as much with the value because it's already clustered together, right? So we already know that we only want 5 years in that whole range of years, and it's going to be even faster. And the gains are going to be way higher the more granular you go, right? So if you go to between 14 and 15, it's going to be even faster, right? So you can see 21 milliseconds, and if you do it again, about around 20 milliseconds. So the more granular you go, so the shortest range, the more it's going to be efficient because you're only querying smaller clusters every time. So I hope you guys enjoyed this video. It's really a video to show you the basics of indexes and how you can use them in your application. If you want me to cover other cases of indexes, feel free to drop them in the comments and I'll make a video on those topics. Otherwise, I'll see you guys in the next video, and I hope you have a great day.